Hello, everyone. Welcome to some additional series on textbooks, and mostly I'm doing physics textbooks. But for this one, I decided to do a series on sort of pure math textbooks. These aren't like from learning math or learning math for physics. I have another playlist on mathematical physics textbooks, but this is just purely for enjoyment. And I really like these textbooks that I'm cover. I own a lot of math textbooks, but this is just a very small selection of just enjoyable books to read, if you have some interest in the topic. My philosophy in mathematics is I don't like the Bourbaki school of French mathematics where it's like definition, lemma, theorem, corollary, new topic. I'm not interested in rigor. I'm more interested in computation and constructive mathematics and learning the basic ideas and its history. And too often these are neglected in the math textbooks. So the books I'm going to show you are books where they spend a lot of time discussing the history, they show computations, they give you the ideas on how they're developed and so on. So with that said, I'll start with one of my favorite first books, which is written by this author, Harold M. Edwards. He passed away, I think, in 2020, but he was, to me at least, I think he was the best writer on math textbooks. And I recommend looking at all of his books. I'm going to give a selection of about 3 here, but he's got a bunch of others. But the best thing about his books is that his philosophy is to show a lot of computations and everything. This book will let you learn a lot about, Riemann's zeta function, and the original paper is given, and he analyzes the original paper for like 37 pages. You have to know complex number theory and analytic number theory to understand this book, but he does the calculations in detail, and he goes all through the prime number theorem, and he does a lot on numerical analysis and everything, and these formulas that were discovered like 50 years after Riemann died, things that he had done, the Riemann-Siegel formula. And again, large-scale computation. And this book is old, so it's not current. It's not up to date. I think it's not from 1968, but it's a great place to start to learn about Riemann's zeta theory. It was republished in 2001 by Dover Books, so you can get it very cheaply, and it's got all good reviews and everything. Okay, the next book I want to go into is also by Harold Edwards, and this was a book I bought a long time ago before Fermat's last theorem was proved. You might think it's out of date, but really this book is sort of, as it says, a genetic introduction to algebraic number theory. If you want to understand a little bit of what algebraic number theory is about in a painless manner, this book goes into it. Basically, he proves all the results on Fermat's last theorem up to Kummer's results in like the 1850s, where he proved it for all, I guess what you call regular primes. But this is a great book because he does all the computation in the book. He does pages and pages of just showing you how unique factorization breaks down in certain number fields and how you can rectify it and everything. And so I just want to show you a little bit about the table of contents. He goes all the way back to the beginning on Fermat's last theorem and proves it for the first few cases, and then he does Kummer's results and this theory of ideal factors and proves Fermat's last theorem for regular primes. So it's really and class numbers and everything. I only read half the book. Once he got to, I didn't read the rest of the book on binary quadratic forms and a lot of these other things, which are also interesting. I may get to one day. But if you want to read a math textbook sort of like how math textbooks should be written. This is one. It gives the history, it gives the computations. It's not abstraction upon abstraction. So I really recommend this book. And finally, the third book by Harold M. Woods that I'm going to recommend is a very short book on Galois theory. And again, he goes through the history, he does the computations, and you can learn, even without having had abstract algebra before, you can learn Galois theory. And let me get to the table of contents. The main thing is that he does the cyclotomic equations and any resolvents and everything, and he just goes through everything. It's only like 100 pages, and he does it in an easier way, and he has a lot of computations on the side. So I recommend this. This is a graduate level textbook, but it's really fairly easy, and it's short. The next book I want to recommend, this is another book, that I really like. If you're into number theory or analytic number theory, this is like an undergraduate book. If you want to see a proof of the prime number theorem, that's what this book does. It does everything through the prime number theorem, and it does it in a straightforward manner. You know, it's like a direct way to get there. And he reviews the necessary number theory, and then he just starts developing some elementary theorems and congruences, and just goes all the way through the primitive roots, and then the proof of the prime number theorem, analytic proof of the prime number theorem. So if you're interested in the prime number theorem, which says that the number of primes less than x is x over log x, natural logarithm of x, I believe. It's a really straightforward book, and it's not abstraction upon abstraction. And another book on number theory, which I really enjoyed, might be a little bit out of date, but if you're interested in how to factor prime numbers and primarily testing, this is an undergraduate book which goes through techniques that I don't believe it does elliptic curve factorization. That was developed probably after this book was developed. It might cover it a little bit. Let me get to the table of contents. But again, lots of calculations in this book. It's a good book. It starts from the beginning, assumes you know number theory, and starts proving a lot of things. Talks about pseudo-primes, the RSA public crypto system. If you're not familiar with this is a great place to get familiar with it. And then various factorization techniques and quadratic reciprocity and quadratic sieve. I think, and he does things on continued fractions, Lucas sequences. He does discuss elliptic curves very briefly. So there's a little bit it's a short book, 200 pages, but if you're interested in the technology of RSA crypto system and how we factor numbers, this is an excellent book to start. It assumes no knowledge of number theory. Another book I have on, which is related to number theory, this is an undergraduate level book, and it treats the very difficult topic of rational points on elliptic curves. So if you have an interest in something like elliptic curves, this is a great book to get an introduction to it, because there's an infinite amount you can write on this, and it's just a lot of computation, a lot of arithmetic and geometry, and he has a long chapter on projective geometry as an appendix to introduce you to that, which is like very rarely taught nowadays. So I recommend this as if you want to have an introduction to elliptic curves. My final book on number theory, I love this book because when Fermat's last theorem was proved, it became obvious that this was way beyond, I'd have to devote a whole lifetime to understanding the proof. But this book actually outlines the proof, and it goes through all areas of mathematics. It's just notes. It's only 200 pages long. It's just sort of like giving you, without details, what was done and why and how and so on. So a lot of it is like just advanced mathematics summarized. It's sort of like a popular mathematics book for people like me who know a little bit of mathematics but aren't familiar with all these things on the graduate level. So he talks about, history and then unique factorization and the elementary methods. I was all familiar with that. And then he goes through Kummer, which I learned from that other book by Edwards on Fermat's last theorem. Then he starts going into recent developments, and he talks about elliptic functions and modular forms and the zeta function and the ABC conjecture and so on. So it's all fascinating reading, even if you're not going to be able to understand the proof of Fermat's last theorem from this book, but you sort of get an idea of how broad mathematics is and how it was all integrated into the proofs. And this is, if you're interested in Fermat's last theorem and you want to have an idea of what was done, this is an excellent book. Now, the next area of interest that I have in mathematics, and I have a lot of different areas, but I was always interested in the foundations, set theory, logic. I always wanted to read Cohen's proof on the impossibility of proving the continuum hypothesis and everything. So one of the best books, I think it's the standard book for learning set theory, is a book by Enderton. He has a great book on set theory, this one, and he has another great book on logic. And this is like as easy as it gets. This is like sophomore level, but it's thorough. It doesn't skip anything, and it proves everything starting from the beginning of set theory in sort of like an informal way and then a formal way. And he does all the axioms and constructions and learn about ordinals and cardinal numbers and well-founded axioms and relations. So this is the place to start on set theory if you don't know anything. If all you know is your high school math on set theory, I recommend this book. And then after you read this book, or concurrently with this book, he has a great book on mathematical logic where he proves Gödel's theorem and everything. And unlike other books which prove Gödel's theorem, he doesn't leave out any details. He proves everything you need to know about every recursive function. And he goes through everything on logic, starting, with propositional logic and then predicate logic. And, then he goes through first order logic, and then he does the proofs on undecidability. And he just literally proves everything you need to know. He doesn't skip anything like a lot of other logic books do. And then, if you've mastered those two books, you can read this great book by, this isn't the book I want. Oh, here it is, Manin. I guess Koblitz updated it after Manin. I have the first edition of this book, but this is a great book on mathematical logic. It says for mathematicians. He actually covers a lot of different topics, but various parts of it are really understandable once you read those other two books on logic and set theory that I just mentioned. And he goes into, his proofs are fast, but he does show the details. But he has a whole chapter on the continuum problem and forcing and constructible sets and everything. And then he has a whole section on computability and the proof of, I believe it's Hilbert's 10th theorem on, recursive functions and showing that there's no way to compute certain things. And then he goes on Gödel's theorem, and he covers all that, and he has a little chapter on model theory. So the thing about his writing style is he has a lot of like asides, and he deviates a lot and comes back and everything. So for those who don't like vignettes on various areas of mathematics and literature and poetry and everything, but he's a great writer. So I highly recommend this book. If you have an undergraduate understanding of set theory and logic, you can understand this book. Okay. Hold Hold on a second. Where am I? Okay. Now I want to turn to, I only have one book here on geometry, but I really love this book. This book is sort of like, not even for math majors, it's sort of like for math teachers and everything. And what it does is it really develops non-Euclidean geometry. It fills in all the holes of Euclid. Hilbert filled in all the betweenness postulates and all the other axioms, and he does it here in this book where he goes through the beginning of Euclid's geometry, and then he talks about the dangers in diagrams and all this other stuff, and he actually gives a complete axiomization following Hilbert and proves everything about the elliptic geometry and then hyperbolic geometry and spherical geometry, and how he's able to show the consistency in everything. He has Hilbert's axioms, neutral geometry where you don't have the fifth parallel postulate, the history of the fifth parallel postulates, and then how non-Euclidean geometry was discovered, and a complete proof of the independence using these models by Beltrami and Poincaré. So this is a really good book, and he extends it with Klein's Uringer program. So I recommend this book if you want to learn about non-Euclidean geometry and in an easy, readable way, and all the proofs and how it was established, and a historical approach. Going on to analysis, there's this great book by Corner. I guess it's being updated soon. It's not. This is like the new edition, revised, but the old edition I have, I think it was published in 1989. But this is one of those books where it's not really a textbook. It's 600 pages of like short sections on Fourier analysis and different applications. And he proves some things, but it's not a proof book. It's, he'll introduce Fourier series, but he'll talk about tides and the rate of convergence. And he's always talking about the edge cases, nowhere differential functions, Monte-Carlo methods, Brownian motion, all kinds of things. And then he'll do differential equations, but he'll also do the thing on showing completeness and orthogonality and Fourier transforms. And then he'll take it into like differential equations and things like that, statistical treatments, and then he'll go into number theory and a little group theory and prove Decadine's theorem on primes in arithmetic progressions. I can never pronounce all these mathematicians' names, so I'm mispronouncing all of them. But this is a great book. As you can see, it's got 110 sections and 558 pages, so it's like 5 pages a section. You can jump around. It's not, you don't have to. And Terence Tao has a preface here where he talks about how, for those of you who don't know Terence Tao, he's like one of the foremost mathematicians today. And he goes, this book is a rare example of one that stakes a middle ground. It does not comprehensively introduce the fundamental definitions and results, but instead provides a sampler of bite-sized and largely standalone examples of how the themes of the subject go. So it's both practical and mathematical context. Highly recommend this book if you want to learn more about Fourier series. I'm not really that big into a lot of like rigorous results and new developments in mathematics, but I felt I had to know a little bit about Lebesgue's theory of integration, and this book, A Radical Approach to Integration, to that theory, is really good because he goes through the whole history of it, why, how, all the oddball cases where the fundamental theorem of calculus doesn't hold, why we need a new way to integrate. Like he starts with the 5 big questions. He does the Riemann integral. Then he talks all about the real numbers and bare category theorems and everything. And then he talks about measure theory and all the historical development. And for finally getting into the new integral and some of its applications. So for physicists, Riemann is good enough, but it's nice to know that there are some reasons why mathematicians went on this more rigorous approach. The next book, this is a short book on probabilistic modeling. There are really many good books on probability. MIT has one. Professor Blitzstein of Harvard has a great book on probability. But this was just a short book that I got a long time ago, which has a lot of interesting models in probability theory. And it develops all the basic things on random variables and probability distributions. And then it has some applications. It's only like 180 pages, and it might be worthwhile to take a look at. The real book on probability is not really on probability theory per se, but it was written by Jaynes, who was like a statistical physicist. And this book was published after he died. It's called The Logic of Science. And the main thing is that he talks about all the interpretations of probability theory and all the things that people don't talk about, plausible reasoning and hypothesis testing and everything, and all the controversies in the 20th century that occurred and everything, and quantum mechanics and everything. So if you want to get something where you already know probability theory, but you want to learn about the philosophy of it and the details, that are being debated in the literature, this is a wonderful book. And it's unfortunate that he didn't get to quite finish it. You can see there are things that are left out. But it's all readable and controversial. And like I said, he talks about other approaches to probability theory and so on. But mainly he's trying to get rid of the infinities and everything. Okay. This was a book I got a long time ago. It's called Reality Rules. Mainly it's like a tour of all like recent developments in mathematics, and I'll get to the table of contents. But he talks about everything, that some topics that you don't see in courses by themselves. Sometimes it's hard to get to the table of contents. But he talks about, models and catastrophe theory, chaos, singularities, all these things. Cellular autonoma, chaos, games, theory of evolution, systems and brains. And so it's all very readable and applied to a lot of things. So it's definitely an applied mathematics book, but it's all these recent areas. And I'll go to the second book on here. This is volume 2. Let me get to this. So here he talks about, again, games theory of, maybe this is volume 1 that he's doing again. But he talks about geometry, structure, art, literature, computation and complexity theory. He goes all the way through that, and then modeling. So this is a very good 2-volume work, very readable, very enjoyable, on the frontier topics in applied mathematics. And finally, there's a book called Mathematics by Experiment. And this is like at the forefront of what they do to now, sort of like if you want to find a formula for a number, or let's say you just get like a 20-digit number and you want to know where does this come from, you can actually, there's software and everything that actually helps you find out. But experimental mathematics is like you don't prove these things, but you sort of show that this is probably true and everything. And it's great things on computing pi to millions of digits, normality of numbers, and various numerical techniques. So it's definitely computer-oriented and everything. And it's like a new field. It's something where they don't prove everything, but they get pretty good showing that it's probably true and everything. So, the idea is to sort of experiment on a computer. Finally, there's many books on mathematics and its history, and Stilwell is a very good mathematical writer, and I recommend this book. Just goes through the history of mathematics, but it proves a lot of things along the way and shows things, whether it's geometry and Greek number theory, and then polynomial equations and that projective geometry. So it goes through all the fields of mathematics and sort of like how they developed and how they were discovered and so on. So it's partially a math textbook and partially a history textbook, but it covers just so many different areas of mathematics. Okay, thank you for watching this video. Again, most of these books are just for entertainment. If you really want to learn abstract algebra or differential equations or topology or modern algebra, commutative algebra, and all these advanced things on schemes. And I just bought a book the other day on ideals, varieties, and algorithms. You know, there's a lot of books out there, textbooks, that are painful to read, the math ones especially. But these are like non-painful to read, enjoyable books. So I'll see you next time. Thank you very much.